Hi, everybody. So this is a quick introduction to some of the physics terms that we're going to be using this year. And I kind of want to have you access this as often as you want throughout the year because these are terms that we're going to be using between now all the way up to June. So, we've had the opportunity at this point to play in the physics classroom and look at a couple of different ways that things are moving. And we've already gotten through the point where we have some vocabulary to attach to those things: constant velocity, accelerated motion, uniform circular motion, rotational motion. But now it's time to get into a little bit more of the nitty gritty, as some of those terms deal with one-dimensional kinematics. So this is sort of the beginning. It's more notes than problems, but I'm going to sort of give you some examples of what we're really dealing with as we go through some of the terminology for the first chunk of the year. So the first thing we need to understand is the difference between a vector and a scalar. And in physics, we have these two items to sort of differentiate quantities, numbers, that we'll see in the physics classroom. So the first thing I want to talk to you about is something that's called a vector. And a vector is any quantity that has a magnitude and a direction. So the magnitude here, the business end of this, is a number, all right? So when we have anything that we can quantify, 10 meters, 23 degrees, of elevation, we're talking about something that we can put a number on, but we can also put a direction on it. And in physics, typically speaking, we're dealing with direction that might be, if you guys remember 7th grade, the cardinal directions, so north, south, west, and east. And typically when we talk about direction in physics, you can say 23 degrees north or 13 degrees west, in terms of looking at a compass, and I guess that's what I'm trying to get to here. But when we're dealing with direction, we also can talk about things in the positive and in the negative direction. So standing in front of the classroom, we'll see that anything that goes to the right hand side is going to be in the positive direction. Anything goes towards the left is going to be the negative direction. Anything that goes down is going to be the negative direction, and anything that goes up is going to be the positive direction. Anything that goes forward is the positive direction. Anything that goes backwards is the negative direction. So that's really what differentiates a vector from anything else out there. I want you to walk 15 paces forward. Well, that means I want you to walk positive 15 paces. And if I want you to walk to the left 25 paces, that means I want you to walk negative 25 paces to the left. So you'll see throughout the year that there are some things that we're going to be doing that have the ability to have a positive and a negative put on them. And all that positive and negative really means is that those are directions that we want you to go in. Positive 25 meters, negative 13 meters, and then we'll deal with compass direction in terms of degrees as we sort of get through that stuff. The other way that we can talk about the other way that we can talk about numbers is through scalars. And that's the big difference, the big difference between vectors and scalars is that scalars are quantities that don't have direction associated with them. So I'm never going to walk up to you and say, hey, give me positive 25 pounds of potatoes, because pounds really doesn't have a positive or a negative connotation onto it. The positive and negative with scalars really just means that we're talking about how much or how little you're dealing with. So, and it's interesting that I used degrees before, because when we talk about degrees in physics, we're usually talking about degrees on a compass or on a protractor. You want to make a triangle that we're going to go up 25 degrees or we're going to go down 25 degrees. And that has a direction to it. The other kind of degrees that we deal with, and goodness knows this week we're dealing with it a lot, we're talking about degrees of temperature. but I'm not going to say 25 degrees Fahrenheit positive means a direction, because that doesn't make any sense. 25 degrees Fahrenheit means it's cold out, not we're going one way or the other 25. And if we say negative 2 degrees Fahrenheit, that means it's really cold out. And if we say it's positive 133 degrees Fahrenheit, that means it's really hot out. So the positive and the negative for a scalar really just has to do with the size or how something feels, hot or cold, or heavy or light. Whereas when we're dealing with a vector quantity, those positives and negatives really have to do with which way are you going, which way are you looking, which way are you walking, which way are you driving, which way is the rocket ship going. That's the big difference between vectors and scalars, and I hope that really makes sense. How do we use those? Well, vectors and scalars sort of dive right into distance and displacement. Distance and displacement are both ways that in physics we use to measure how far something is away from you or away from where it starts. And both of these, the unit for both is meters. And meters, for those of you who don't know, it's about 3 feet. It's a little bit more than a yard, 1 meter. It's 39.36 inches. But for the physics world and the rest of the world, actually, besides the United States, they measure distances in meters, kilometers, centimeters, millimeters, nanometers, micrometers, picometers. So it might be a good idea to review your old, even back to biology, that step chart that talks about, how many kilometers are in a meter, how many, we have to look at the prefixes, the Greek prefixes again. But to talk about distance versus displacement, the distance, when we're dealing about a distance, is the total amount of traveling that you did if you added each piece of it up, ignoring the direction. And the big idea here is distance is a scalar. And that's a really, really weird definition, and I don't want you to get freaked out by it. I want to go back to... it's a scalar. I don't want you to get freaked out about it, but I want you to think about gym class when we talk about distance. And I'm going to give you the first taste of my lack of ability to draw. You go to gym class and we make you walk the mile, right? Or run the mile. And in reality, you start here, you go around the track badly, once, twice, 3 times, 4 times, and you stop right there. Now, how far have you run? Start to finish, adding everything together, how many steps you took, you have run a distance of 1 mile. But you started here and you ended here. So what we would say about your displacement is the amount you move from start to finish. If you move that far in 1 step, you started here, you stopped here, your displacement was 0 meters. You didn't move start to finish. Now between the start and finish, you went a full mile. You walked, you ran around the track 4 times. You worked up a sweat. You killed some calories. It was your heart loves you for it because you actually did distance. But start to finish, Mr. Mazzulli started the stopwatch and he didn't move. And you went around 4 times. And then Mr. Mazzulli stood at the starting line and stopped the stopwatch. He and you, from start to finish, displaced 0 meters. And you might have run for a mile, but at the end of the day, you displaced 0 meters. Another way I like to think about this is, what's your displacement for an entire day? Well, for me, I wake up in my bed at 5:45 in the morning. I go to Milton, I drive, I go to golf, I walk a golf course, I do all this other stuff. I walk around the building, I go to the supermarket. These are all distances that I'm going between the hours when I wake up and when I go back to sleep. And that's all distances that you could add together. How far did I go in the day? I don't know, 25 miles, 30 miles. But the displacement from the start of my day to the end of the day. I woke up in my bed. I went back to sleep in my bed. It's the same bed. I displaced 0 meters for the whole day. And this gets to be sort of important in physics because as we're going to do some problems, I'm going to get rid of this little shady thing. We might tell you, well, I started here, I walked 10 meters this way and displaced positive 10 meters because we're going to the right. And then I positive displaced in the y dimension another 7 meters. Okay? So x dimension, y dimension, I'm going across and then I'm going up, and we'll do more of this later. So how far did I distance? What was the distance I traveled? Well, 10 meters plus 7 meters, that would be 17 meters. But how far did I displace? And to figure that out, I hope you remember a little bit about your math, a little bit of trig. From start to finish is from here, the beginning, to there, the end. And I'm hoping that we did that triangle sheet last week a little bit, and I'm hoping that you remember a little bit about how to solve for this. 10 squared, I would use Pythagorean theorem. 10 squared plus 7 squared, that's going to be 149, and the square root of 149 is going to be 12.2. So how far did I go in distance? 17 meters. I took 17 meters worth of steps. But from start to finish, I displaced myself 12.2 meters, and we would usually put some sort of a degree, and I'm going to put a theta, degrees there. We would put an angle there to tell us in which direction we displaced ourselves. So I hope that sort of opens your eyes to what the real distance or difference between displacement and distance is as we go through. Speed versus velocity. This is another vector versus scalar thing. Speed is how fast you're moving, and there's no direction to it. It's measured in meters per second because you have a distance and you have a time, and it's just like you look in the car and you look at the speedometer, it's telling you in miles per hour how fast you're going. So we're dealing with speed. This is most definitely a scalar. Okay, it's a scalar. There's no true direction to it. But if we were to look at velocity, the velocity is not just how fast you're going, but also in which direction you're going. Now, the crazy thing is the unit is the same for both of them, but we would also put in an added direction. And it could be, 25 meters per second to the east, 10 meters per second to the north. You could put a cardinal direction in. Or as we said before, you can put in a positive or a negative. I'm going positive 25 meters per second or negative 17 meters per second, whether or not you're moving forwards or backwards or left or right or up or down. Okay, so this is a big deal. And you'll see when we start getting into some of the math, this gets to be a very important distinction to actually start working with. So what happens when our velocity is changing? Well, what happens when our velocity is changing, we call that acceleration. Okay, and acceleration is really the rate at which you are changing your velocity. And for most of us, we think that our velocity is our speed. And that's partially true. When we accelerate, you guys know that you're either speeding up or you're slowing down, because that's one way that we change our velocity. We're changing the meters per second that we're going. So for starters, acceleration is, the unit is meters per second squared, so that's important. But there's another way that we can change our velocity. We can speed up, we can slow down, but we can also accelerate and change our velocity by changing our direction. So if you start by going north, and then as time goes by, you start going towards the east. You were going this away, and now you're going that away. And that is a change in direction. And this delta, this triangle always means change in. So that change in direction is also a way that you can accelerate. Okay, acceleration. So there are really three ways you can accelerate, and this is really important. You can either speed up, you can slow down, or you can change your direction. By the time you get out of here in May or June for juniors and seniors, you're going to be able to figure out something's acceleration by either looking at how much they're speeding up or slowing down, or how quickly they're changing their direction. And the way that, this is sort of interesting, if you've ever been to an amusement park, most of the fun rides happen because you accelerate. And yeah, you go on a roller coaster and you start by going really slow, and then you go really fast, and that's fun. But if you've ever been on the Turkish Twist, or if you've ever been on one of those the Brain Scrambler, you sit in something, and you're making really, really tight circles. And those really tight circles are happening because you are changing your direction. And that gives your body an interesting sensation, and it's fun. It sort of makes your stomach drop. And some of us really enjoy that. So that's sort of the deal with acceleration. I hope that makes sense. And finally, the last little vocab word I want to give you is time, that we talk about in physics. And time is always measured, in physics at least, in seconds. Okay, notice I never said miles per hour, I always said meters per second. So time, you're going to be measuring a ton of different experiments and things that we're going to do in physics. You're going to need time quite often. And we're always going to measure it in seconds. We very rarely use hours or minutes. But time, the technical definition for time is just how long it takes something to happen. If I drop a ball, I want to time how long it takes for the ball to be released from my hand until it hits the ground. If I want to time how long it takes to make a trip, I want to know how much time passes between when I leave my house at 11 o'clock and I get to, New York City at 3 o'clock. I want to know how much time has passed in seconds. So, that's sort of why I gave you that primer last week, using all those dimensional analysis tools to make sure that we can convert meters per second to miles per hour to miles per minute and miles per year, because those are things that we're going to have to be doing. All right. But time is really the most non-complicated old thing we've ever dealt with. Okay. So I hope that sort of breaks a couple of things down for you. And our next video, I'm going to start helping you look at different scenarios where we're going to have to do some calculations. Okie dokie.